Say we have a function f of x comma y is equal to z, where z corresponds to the height of whatever two inputs x and y you put into this function. Now, if you were to represent a point on this function, it would be x comma y comma z is equal to x comma y comma, well, f of x comma y, right? We said that was equal to z. And so, if we express this as a vector valued function, well, it would look something like this, where you effectively, instead of having one output of your function, you instead have the whole vector as the output of your function. And more conventionally, you use u and v to represent all the components x, y, and z of your function. Let's say that we're dealing with a surface u squared plus v squared, and we want to find the surface area between those two bounds. The parameterization of this surface is given by that. And so notice how when I move along the u direction by a little bit, that causes a change in the resulting vector in the surface. And the difference vector seen in the red is given like that, because we've only made a tiny change to u, keeping v constant. Well, we can do the same thing for v. As we take a tiny step in v direction, keeping u constant, well, the difference vector in the red is represented like so. Now, notice how we're kind of tracing along this curve, but when I multiply those two difference vectors that I got, those two red vectors, well, I am kind of approximating that surface area, right? Or am I? They form a parallelogram, not a rectangle. What do I do? Let's go back to derivatives. So recall that this is the definition of the derivative, and if I multiply delta u on both sides, I get that this difference vector that I get is equal to derivative with respect to u times delta u. And I can do the same thing for v, right? I can say that this difference vector that I got from v is equal to derivative with respect to v times delta v. Now you can see that these two difference vectors, they form a parallelogram. So I can't just multiply them together to get the surface area of a tiny region and then sum it up with an integral. I can't do that. I need another way to find out the area of the parallelogram, and luckily we have linear algebra. Let's say if we have a vector A and vector B. Now if I take the cross product of these two vectors, that gives me a new vector, which is orthogonal or perpendicular to the two vectors and obeys the right-hand rule. But more importantly, the magnitude of this vector gives you the area of that parallelogram that we were searching for. And this is exactly the tool that we use for our difference vectors. Going back to my difference vectors, the cross product of them can actually be written as this form. This is actually one of the properties of it. And so if we want to sum up all of these surface areas across our u boundary and our v boundary, well then this just turns into a double integral problem. And what you are basically doing is for every step along the u and v direction on your bounds, you are calculating the surface area of that one small difference vector piece, and you do it for all the tiny difference vectors that you make across the entire surface, and you sum them all up. Great, now that you have the general formula down, suppose that you're trying to find out the mass of our surface instead of just the surface area. And suppose that the density of every point on our surface is given by the following function, f of x comma y comma z. Now, of course, we've reparameterized our curve, which means we can do the same parameterization for this function right here that represents the density at every point. And so we recall that, well, density is equal to mass divided by volume. If I multiply volume on both sides, I get that the volume times the density is equal to the mass. And in this case, because this is a surface, the volume is going to be substituted for surface area. But the point is that we can multiply in our integral the surface area by the density at that specific region. And so if I multiply the density at that specific UV value by the surface area given by this UV cross product, well then I get the mass after I summed up everything. Recall that this is only a scalar field, because something like density, it only assigns a density value per point, right? It's not something like a vector. But if we were dealing with a vector field, well then, if I incorporate it into the formula, it actually determines something called the flux, which is the amount of sort of, you can think about it as vector, that kind of flows out of a surface. And so what you have to do is, instead of simple cross product magnitude, you actually have to take the dot product between the vector at that UV region and the cross product.